Right, welcome back. So the last time we were looking at the chain rule, that is, we gave some intuition about the chain rule. We looked at two examples, one of a particle moving, let's say a mosquito moving in a room, and changing Cartesian coordinates to polar coordinates and seeing how the derivatives look like in polar coordinates. So using this intuition, we can we actually stated the chain rule as a rigorous theorem and then started proving it. So let's recall what the statement is. So this is the chain rule. Be two functions f of a is an interior point of B. If f is differentiable, at A and G is differentiable at B, at f of A, then the composition G composed with f is differentiable at A. Moreover, the derivative of G composed with f, this matrix, is this. So this is the direct analog of the one variable chain rule, which if you recall is GOF dash of A is G dash of f of A, f dash of A. Yeah? So in more than one variable, it's simply just a direct analog. The derivative matrix of this is the product of the derivative matrix of G and f evaluated at appropriate places. So it's very easy to remember the chain rule, right? And the hypotheses are also very easy to remember. For this to be differentiable, obviously you would want the derivative of G to be differentiable and f to be differentiable at appropriate points. And differentiability makes sense only on interior points, so these two must be interior points. Yeah. So nothing very shocking about the statement of the chain rule. This is in the sense of multiplication of matrices. Right. So how does one prove it? You simply follow the intuitive idea, but keep track of the errors. So the last time we first noticed that suppose this is A, this is B. If you take a point A here, because it's an interior point, you have a small ball around it. You have a small ball around this. This is of distance of this is epsilon 1. This is delta 1. And the image of this small ball lies somewhere inside. That is, this maps to this via f, right? This is the image of this small ball. So we choose delta 1 to be so small so that this happens. Next, we define the errors as usual. Notice that the error will depend on h, likewise the error for the second function will depend on, let's give this a name, let's call b as f of a. B plus h tilde minus g of b minus the derivative, right? Now, by definition of differentiability, this we agreed that the last time that by definition of differentiability for epsilon positive, you can assume this is less than 1 without loss of generality, because if you manage to, so what do we want to do at the end of the day? So what is it that we want given epsilon? Yeah, there exists a delta so that the linear approximation holds. G composed with f of a plus h minus g composed with f of a minus dg at f of a times df of a multiplied with h divided by norm h is less than epsilon whenever 0 is less than norm h is less than delta, and of course h is an a. This is what we want. We are heading towards this aim. Now the point is, so you want this to be less than epsilon, you want to choose some delta small enough so that this is accomplished. If your epsilon that you're given is larger than 1, no problem, choose some epsilon which is less than 1. If this is less than that epsilon, surely it's less than the epsilon that you gave me, right? So without loss of generality, you can assume this. Now, by definition of differentiability, there exists a delta 2 which we can assume to be less than delta 1, which is further less than 1, such that delta 2 of h tilde is less than something times h tilde. Last time we wrote down what that something was, but this is an overkill. We don't really need such a complicated expression, as we will see a simpler one will do, but I just wrote this down simply because. So we can call this epsilon tilde for now, and we will deduce what this epsilon tilde ought to be. It must be epsilon divided by something. What is that something? We can deduce later as we go along the proof. As I said, this is an overkill. We can make do with something simpler, but you know, inequalities, they're very ambiguous beasts, right? I mean, you can use a different set of inequalities and I can use a different set of inequalities and so on. So sometimes it's better to be safe than sorry. That's why I use this overkill. But for now, let's call this epsilon tilde. Whenever, when does this happen? If h tilde is less than delta 2, right? So this is by definition of differentiability of G. By definition, the delta 2 of h tilde is less than whatever epsilon tilde you want times norm h tilde, provided norm h tilde is small enough. It's less than some delta, and you can choose the delta to be smaller than delta 1. If it's not already smaller, simply choose the minimum of delta 1 divided by 2 and the delta that you came up with. Okay. So let's proceed. So we'll keep track of these errors and proceed. Now the point is g of f of a plus h. Recall, what is it that we want to do? We want to, let's go back again, we want this. So we want to first look at this, right? And we want to say that this is approximately equal to this plus something else, and the approximation can be made precise in this manner. So that's why we are looking at this difference. Yeah, it's important to keep track of what we are doing. What is f of a plus h? F of a plus h is of course f of a plus the derivative of f acting on h plus the error term. Yeah? So this is f of a plus h, which is g of b plus this plus the error term minus g of b. What is g of b plus anything, right? We can give this a name. Let's say we call it h tilde. What is g of b plus h tilde? It is g of b plus the derivative of g at the point b multiplying h tilde plus the error term minus g of b. These two get cancelled out. So you get the derivative of g of b. What is h tilde again? Let us write it in its full glory, so to say. Plus delta 2 of h tilde. Okay? Right, I mean delta 2 of h tilde is also, maybe we can write this also in its full strength. H tilde is actually this, but I'll just still call this h tilde here for the purposes of the next step. Right, so what do we want? We want to take g of f of a plus h, minus g of f of a minus this part. This is the linear approximation. This equals the derivative of g of b, this matrix, times delta 1 of h, plus delta 2 of, let's call this h tilde for now. This is by the triangle inequality, which is our best friend, as I said. Derivative of g of b times delta 1 of h plus h tilde. Now again, these norms, this is, what norm is this? This is the usual norm obtained from Pythagoras theorem, or in other words, if you want to use a fancy name, it's the L2 norm. Now with these L2 norms, the L2 norm behaves well with the Hilbert, with the Frobenius norm. In any case, the point is any matrix norm would satisfy this property. We've already done this earlier, by the way, but I'm just recalling this little concept. If you multiply a matrix with a vector, then this is less than or equal to this particular thing. Okay? Just recall that if you take any matrix, multiply by a vector, it's less than this if you choose appropriate norms. Any matrix, now so let's say L2 norm, this is the Frobenius norm. What is the Frobenius norm again? The Frobenius norm is simply taking the mod square of each entry of the matrix, adding all of them up and taking the square root. Okay, this follows from the Cauchy-Schwarz inequality. Right. Okay, so let's keep this in mind. Let's go to the next page, so to say. Let's rewrite this. Yeah, so this is less than, again, what do we have here? This dg times delta 1 plus delta 2 of h tilde. Right. Okay, now that's fine, but what is delta 2 of h tilde, right? How can we estimate this? We already know that this is less than, in fact this is strictly less than what is delta 2 of h tilde less than, let's recall, let's go back. It's less than some epsilon tilde times norm of h tilde, right? It's less than epsilon tilde times norm of h tilde, provided if norm of h tilde is less than delta 2, which is of course less than delta 1 and 1, right? That is, if, what is h tilde again? H tilde is df h plus delta 1 of h, and we want it to be less than delta 2. Yeah? Okay. So, now this, all right. So, notice that what can we do at this stage? First of all, how can we make sure this happens? And how can we estimate this term? So, firstly, notice that if, let's say, if we assume that, so let's, by definition of differentiability, of f at A, what do we see? We know that the error term can be estimated like this. Okay, it can be less than, let's say, epsilon double tilde. What must epsilon double tilde be? I claim that epsilon double tilde being 1 is good enough, but let's call it epsilon double tilde, and let's decide what it ought to be as we go along the proof. Let's discover rather than just state things, right? Whenever this h is smaller than delta 3, which can be assumed to be smaller than this, right? But it's not just this, we also want this to be less than delta 2, right? So, how can we manage that, right? So, what we want is, so we also want to estimate this, yeah? So, this is less than, by the triangle inequality, which is further less than this. Which is which can be assumed to be less than delta 2 if delta 3 is actually chosen to be, this is going to be less than 1. Delta 3 is chosen to be less than, let's say, delta 2 divided by plus 1, right? So, what I am saying is your norm h is smaller than delta 3, and delta 3 is so small that it is actually less than this much and so small that this also holds. Okay? So, norm h is so small that simultaneously this happens and this happens. Yeah? So, I hope this is clear. So, let's move on and proceed to estimate this part. Yeah. So, in other words, is less than norm dg B. What is delta 1 of H less than? It's less than epsilon double tilde times norm H. Right. And plus epsilon tilde times norm H tilde. What is norm H tilde? So what is norm H tilde? It is this, right? Which we already know is less than this. So let me copy this down from here. Plus epsilon tilde times epsilon double tilde. Maybe I'll write it like this. Norm H. Yeah? Right. So in other words, this is and we want this to be what? We want this to be less than epsilon. We want to be less than epsilon, right? Okay. Yeah, so that's what we want, right? So what should we choose epsilon tilde and epsilon double tilde to be, right? So suppose you choose epsilon double tilde to be, for instance, epsilon, let's try epsilon tilde to be simply equal to epsilon, and this to be, let's say, by 2, for instance, which is of course less than epsilon itself, because we want this to be, I mean, we can choose it to be even equal to epsilon if we want to, because recall this is, we only want it to be less than 1, so we might as well choose it to be equal to epsilon. And this can be chosen to be so suppose we tried this, right? This is not good enough, yeah, because, and let's say this is less than 1, right? So this is also going to be less than 1. So let's try if this is less than, this is good enough or not. So when you substitute it here, you'll get that this is less than times epsilon divided by 1 plus dfa plus dgb plus, what is epsilon tilde? It's simply epsilon itself, plus epsilon double tilde, well, whatever it is, it's certainly less than 1. So this is epsilon times 1 plus norm dfa plus norm dgb divided by 1 plus norm dfa plus norm dgb. So these two cancel out and this is equal to epsilon. So in other words, by making this choice and this choice, we can ensure that indeed, and if h is sufficiently small, we can ensure this happens. So we are done. Okay? So we are done. Notice that our original choice, namely this, was much too small. We didn't need the 100, we didn't need this and so on. But this is just to be on the safe side, right? We could have guessed at this and proceeded, and we would have found that this would have been good enough. See, at various points I use various inequalities. Depending on what inequalities you use, you might have required that, for instance. Okay? So this is the proof of the chain rule. All we have done is carefully kept track of the errors made in the linear approximation. Yeah? So that's great. Now that we have the chain rule, we can now rigorously justify this. So for the sake of argument, suppose t goes to this is differentiable. Is differentiable on R. Let's say xyz goes to is well defined and differentiable on all of R3 for simplicity. Then by the chain rule, let's call this g of t. G of t is differentiable on R, and the derivative of g of t is the product of the derivative matrices. And the derivative matrix of this function is what? It's the gradient of the first component, second component, third component. What's the derivative matrix of this function? There is only one component, so it's just the gradient of it. So it's dt by dx. This row matrix, this is a column. This is what? This is simply g dash. So this is dt dx, x dash plus dt dy, y dash plus dt dz, z dash. Yeah? So this is how you can rigorously derive what we did earlier. Right. And one more rigorous derivation. For example, if you take, let's say, you take r comma theta to r cos theta and r sin theta. This is obviously differentiable on R2. You don't need it on all of R2, but might as well, right? And let's say you take x comma y goes to f of xy. You don't need these parentheses. Assume it is differentiable on R2. Then by the chain rule, r theta goes to g of r theta, which is f of r cos theta, and f of r sin theta is indeed differentiable on R2. And the derivative of g is the derivative of f at this point times the derivative matrix of this map, which is the gradient of the first component and the gradient of the second component, right, which is df by dx, df dy times this, and this is exactly what we expect the answer to be, right? So this is fx cos theta plus fy sin theta and minus fxr sin theta plus fyr cos theta. Okay? Right. So this this sort of completes the loop, if you will. All right. Let's stop here. We've done the chain rules proof, and we've seen a couple of examples. where we recovered things. So we'll continue with the chain rule the next time. Thank you for joining.